All right, welcome everybody. So in this video, I want to define what singular values for an m by n matrix are, and then walk through an example about how we can find and identify the singular values of a matrix before moving on and discussing what is the singular value decomposition for a matrix. So let's let A denote m by n matrix. So A does not need to be a square matrix. But recall that we can consider the matrix A transpose A, which is going to be a symmetric square matrix. And we've proven that the eigenvalues of the matrix A transpose A for any matrix A are going to be non-negative. So let's order those eigenvalues, lambda 1, lambda 2, up to lambda n in descending order. So lambda 1 is the largest eigenvalue, lambda 2 the second largest, lambda n is the smallest non-negative eigenvalue. Okay, so these are all greater than or equal to 0. So the singular values are going to be defined as the square roots of the eigenvalues of the matrix A transpose A. So we typically denote these singular values with the Greek letter sigma. So we would say sigma sub I is equal to the square root of lambda sub I. And we don't get any trouble taking square roots of these eigenvalues because we know that all of the eigenvalues of A transpose A are greater than or equal to 0. So the singular values are just a fancy word for saying the square root of the eigenvalues of A transpose A, because that's a lot to say. So it's much easier to just call them the singular values. And so let's take a look at an example of a matrix and see how we can identify the singular values of that matrix. Okay, so let's consider the following example. We would like to find the singular values for the 2 by 3 matrix A, whose first column is 4, 8, the second column is 11, 7, and the third column is 14 minus 2. So the singular values are related to the eigenvalues of the matrix A transpose A. So the first thing that we would want to do would be compute the product of A transpose A. So in this case, we get a 3 by 3 matrix back, which is symmetric. And so we've got first column of A transpose A is 80, 140. The second column is 100, 170, 140. And the third column is 40, 140, 200. So we've got our diagonal entries, and then we have these off-diagonal entries, which appear in pairs. That's a symmetric matrix. So first we compute the matrix A transpose A. Then we go ahead and find the eigenvalues of this matrix. So this is a 3 by 3 matrix. We could potentially have 3 different eigenvalues, and in this case, we do. So you can find the characteristic equation for this matrix and find the roots of that characteristic equation. And so the 3 eigenvalues in descending order are lambda 1 is 360, lambda 2 is 90, lambda 3 is 0. So all 3 of these eigenvalues are indeed non-negative. The last one actually equals 0, and that may happen. So then the singular values are defined to be the square roots of each of these eigenvalues. So the first singular value for A would be the square root of 360. The next one is the square root of the next largest eigenvalue, so that would be the square root of 90. And then the third and final singular value is the square root of the smallest eigenvalue, which was 0. So the third singular value for matrix A is 0. So matrix A has 3 singular values: the square root of 360, the square root of 90, and 0.